Hello everyone. In the last lecture we looked at the management and legislative context for implementing e-flows for dams. Now let's consider the engineering techniques and technologies to actually deliver e-flows. For this lecture I'll rely primarily on these two documents. The chapter on the right, which is from 2017, is one of your required readings. It's by Gregory Thomas of the Natural Heritage Institute. He's also a co-author of the report on the left and head of the Global Dam Reoptimization Initiative. I've included an excellent video presenting this initiative as part of the additional resources for this unit. Before we look at the technologies, let's put ourselves briefly in the mind of the dam operator to consider different motivations for flow releases depending on the objectives and purposes of the dam and reservoir. Also consider that for a storage dam, the operator is thinking about managing both the reservoir level as well as the releases. For a run-of-river dam, the operator is more dependent on the incoming river flow. Withdrawal points for water supplied by the dam may also be at the dam site itself or further downstream. The operator of a storage dam will have an annual or even interannual perspective of capturing and storing water during wetter portions of the year for use during drier months. If flood control is among the purposes of the dam, the operator will try to enter the wetter months with reduced reservoir levels and thus greater storage potential. Capturing maximal wet season flows will be especially important when irrigation is an objective, because agricultural water demands peak during the dry months in year-round agricultural systems. Water supply for domestic and industrial uses will be more uniform throughout the year, but will likely also increase during dry months. Hydropower demands show seasonal peaks during the coldest and hottest parts of the year when electricity is used for heating and cooling. If wet and dry seasons correspond to winter and summer respectively, energy prices may also vary with season. Prices will generally increase in drier months when water to generate power could be limited. Water for irrigation and domestic or industrial supply may also be delivered on weekly or daily timescales depending on the level of intermediate storage water providers possess. The highest resolution temporal variability in water demand comes from hydropower, which varies on hourly timescales. Because electricity generated at hydropower plants is delivered to users at near the speed of light and storage is limited in the system, the variation in demand depends on the rapidly changing needs of the users. Peak hours are in the morning when inhabitants of cities are waking up and switching on lights, as well as afternoon and evening hours when they return home from work. To address these needs, the dam operator may need to change releases dramatically throughout the day. This leads to an ecologically hazardous process called hydropeaking, and we'll discuss how to cope with it in this lecture. For recreation, the dam operator may be thinking about reservoir levels best suited for swimming and boating, or downstream flow releases best suited for whitewater rafting or kayaking. And finally, there's the environment, which we've learned has potentially highly variable flow requirements, but which the dam operator wishes to simplify to some minimum flow when other downstream releases are not required, and perhaps an occasional high flow pulse. What a complicated array of potentially convergent and divergent motivations for flow releases that are affected by the amount of storage available, the timing and degree of consumption of each demand, and the final integrated flow regime extending downstream to the next reservoir and flow control point. Try to keep this complexity in mind as we consider one by one the different techniques and technologies available to meet our e-flows objectives. So what options does the dam operator have available to control water releases? The most basic and universal release feature of any dam is some form of spillway or intake. The spillway may be positioned at any level in the dam, but most will provide the operator with the ability to release flows under most reservoir level conditions. Even better, as we'll see later, is the presence of multiple spillways at different levels in the reservoir. For hydropower reservoirs, there will be a penstock to transfer water from the reservoir to the powerhouse where it can spin a turbine to generate electricity. Water exits the powerhouse and returns to the river via the tail race. Larger dams will have multiple turbines, ideally of different sizes to allow for different flow releases depending on the turbine used. Increasingly, dam operators are placing turbines even on the continual minimum flow released. When fish passages are present, their flows should also be considered, although they're generally quite small. This combination of spillways, penstocks, and fish passages provides the dam operator with options for releasing downstream flows in ways that meet multiple objectives. An active area of research on dam and reservoir operation is the optimization of releases to meet multiple objectives, including environmental objectives. I've included a 2008 paper by Yeager and Smith in your reading if you'd like to explore this more deeply. I mentioned that it's ideal if dam operators have the option of releasing water from different depths in the reservoir. This is important for controlling the temperature of downstream flows. Reservoirs become thermally stratified, with cold water accumulating at the bottom and layers of increasingly warmer water above. Temperature is an important variable in river ecosystems. Species are adapted to natural temperature ranges, and seasonal changes in temperature may cue different sorts of behavior or hormonal processes. When dams release water at temperatures inappropriate for the season, they disturb ecological processes and may even kill species. The most well-studied of these temperature effects relates to salmonid species, which require cool to cold water temperatures year-round. This is a photo of Shasta Dam and Lake in California. If you look closely at the dam, you'll notice intakes at different levels. This enables the dam operator to control the temperature of releases. During the spring months, when water temperatures are coldest, the operator will release water from the upper levels of the reservoir. But over the course of the summer, as temperatures rise, water will be released from greater depths. This operational approach has had beneficial effects on downstream fish populations and ecosystems. Returning for a moment to this slide, we should also recognize the importance of sediment discharge from dams and reservoirs. The accumulation of sediments in reservoirs is a global issue, leading to losses of reservoir function and sediment starvation of downstream reaches, deltas, and coastlines. Sediment removal from dams is a difficult issue, quite different from flow releases. Let's have a closer look at it. Along with the maintenance of downstream flow regimes, best practice in river management requires maintaining sediment regimes. You learned the importance of this in past units. Condolf and others in 2014 distinguished among three broad categories of methods. First are those that reduce sediment yield from upstream, ideally by reducing sediment production at its source and conserving upstream soils, but also by implementing measures to trap sediment above the reservoir. This helps to avoid losses in reservoir function, but it does little to address downstream impacts. A second category of methods has the goal of routing sediments around and through the reservoir. This is extraordinarily challenging and an active topic of engineering research. I'll say more about it in the next slide. And finally, there are methods to recover storage volume. These consist of mechanical excavation methods that are fairly straightforward but expensive, as well as hydraulic excavation techniques that also have their limitations. The paper by Condolf and others, as well as the more general paper by De Halon and others, are in the additional reading folder, so you can delve more deeply into these issues of sediment management and reservoirs. Dam builders clearly take this seriously, as demonstrated by the photo of sediment sluice gates at Three Gorges Dam. The illustration on the right shows a sediment bypass tunnel, which is the vision of future best practice in sediment management. Flushing reservoirs is problematic because coarser sediments are deposited at the upstream edge of the reservoir, far from the sluice gates at the bottom of dams. So the goal is to redirect and transport sediments from the reservoir inlet beyond the dam to downstream reaches. Much work is still required to accomplish this objective, and downstream flows must also be managed to facilitate the continued downstream sediment transport. For the remainder of this lecture, I'd like to mainly focus on issues related to the operation of hydropower dams for both energy production and e-flows. Both of these purposes require variable flow releases, but usually of very different magnitude, frequency, timing, duration, and rate of change. These photos show an example of downstream flow changes due to hydropeaking. As I mentioned previously, hydropower plants are often operated to supply more water at peak hours, turning on and off depending on the electricity demand. This leads to rapid and short duration changes in flows that maximize energy production when needed, but harm ecosystems. Restrictions may be placed on the degree of flow variation allowed during hydropeaking. This is text from an Austrian ordinance, which restricts anthropogenic fluctuations in water flow to a maximum factor 3 change between the low and high flow values of a surge. It also requires that the proportion of the bed covered by water not change by more than 20% from the high water mark to low water points in the surge. Rules such as these help to limit the ecological impacts, but certain river communities may still be affected. The most dramatic ecological impacts include the stranding of fish on riverbanks as river levels rapidly decline. Another less visible impact is shown in this figure from one of your readings. It recognizes that river margins are the primary egg-laying sites for large insects, and repeated wetting and drying of these margins severely limits the abilities of these insects to breed. As you remember from Unit 8, insects are an important living component of river systems, and disruptions to their populations affect other organisms through food webs and other forms of species interactions. The paper by Kennedy referenced on the screen suggests that the impact to insects could be greatly reduced by halting hydropeaking on weekends during the egg-laying season of insects. Weekends are also generally a time of reduced electricity demands. They note that a single female insect may lay hundreds to thousands of eggs, which hatch over a period of days to weeks. So providing stable flows along river margins, even 2 days out of each week, may be sufficient to restore their numbers. But even with the best efforts of dam operators to optimize their flow releases, it's often impossible to simultaneously meet both e-flows requirements and energy production targets. In such cases, additional engineering interventions may be needed. One option is the construction of re-regulation or after-bay dams. These are constructed at or just downstream of the tail race of the hydropower system and must have a storage large enough to modulate the degrees of flow alteration caused by releases from the upstream dam. In this combined system, flows from the upstream dam can be released to maximize hydropower generation, while flows from the re-regulation dam are released to meet e-flows objectives. Additional power can also be generated from the releases of the re-regulation dam. This approach still results in a reach of altered flow, which impacts connectivity in the river system, but alterations to longer downstream reaches can be minimized. A similar opportunity for re-regulation is presented when there are multiple dams on the same river. In this case, the operation of the dams can be coordinated in a way that maximizes energy production in upstream dams while using downstream dams for re-regulation. Learn more about this approach from the video of the Global Dam Reoptimization Initiative. This and other approaches to revising hydropower dam operations will likely require additional changes in the power generating grid, such as construction of additional power plants to compensate for losses in hydropower generation. This approach clearly requires cooperation among the dams involved, which is difficult if each is owned and operated separately. The coordinated operation of dams at basin scales is an active area of research, negotiation, and demonstration efforts. A final approach to smooth out the demand-driven variability in flow releases from hydropower dams is to implement pumped storage. As with the use of re-regulation dams or cascades of dams, pumped storage requires the construction of at least 2 dams, one off the river channel and at a higher elevation than the other. In this system, electricity is generated continuously by releasing flows from the lower dam, perhaps even with a variability favorable for E-flows delivery. When electricity demands are high, the produced electricity is sent to the grid. But when electricity demands are low, the energy produced is used to pump water from the lower reservoir to the higher reservoir. Water stored in the higher reservoir can then be released back to the lower reservoir during peak demand hours, generating additional electricity in the process and augmenting the power delivered to the electrical grid. This is a means of storing hydropower produced during low demand periods for use during high demand periods, and the efficiency of the process is 70 to 80%. Use of this approach is being promoted in different parts of the world, but especially in North America and Europe. All techniques involving multiple dams, of course, come with high price tags, which will limit their application. So we've covered a variety of techniques and technologies to enable E-flow's implementation in the operation of individual or multiple dams, and you can find much more detail in the readings, websites, and videos on eCampus. For take-home messages, remember that dam operators are motivated by a range of demands and objectives related to the purpose of the dam. Optimizing dam operation for E-flows will greatly impair its ability to deliver on other objectives, and this makes reoperation difficult. Dams with multiple means of releasing water and sediment will have greater flexibility to meet multiple objectives, but even when applying advanced optimization algorithms, it will frequently not be possible to meet all objectives satisfactorily, especially between hydropower and E-flows, which both require variable flows. Additional engineering interventions involving re-regulation dams or coordinated operation of multiple dams provide a means of emphasizing E-flows and the releases of lower dams, but this is also costly and may lead to reductions in power generation. And finally, pump storage is growing in use and provides a means of storing hydropower when releasing flows during periods of low and high electricity demand. The stored water can then be used to generate additional electricity during high demand periods. The range of implementation techniques and technologies presented show that dams can be operated in more sustainable ways that also provide for E-flows. But the application of these techniques is expensive and requires years of pre-planning and continued commitment. In the next lecture, we'll look at basin-scale implementation of E-flows, which also considers ways to minimize the need for dams. That's the end of this lecture. Thank you very much.